Philbur Cafe, barista Thomas Bays. May I help you?
Yeah, I'd like to order a Bayesian simple linear regression, please.
Would you like a latte, macchiato, mocha, flat whites, K-cup,
Hold on,
cappuccino?
did you say K-cup?
I meant to say multiple linear regressions.
A simple linear regression will do.
Greetings, BIOS 6618. In this lecture, we're going to apply some of that general Bayesian knowledge to a Bayesian linear regression. We're going to first introduce our motivating data set from our Frequentist multiple linear regression and remind ourselves of the results we saw then. We'll then look at three different prior specifications, both non-informative, quote-unquote, and informative, as well as a nonsensical, poorly specified prior. So let's jump in. Now, we're using this lung function in children data set that we've followed along for various lectures in the past. Just as a reminder, the objective of this study was to describe how lung function develops in children and how smoking may affect that development. The design of the study was a cross-sectional survey of a random sample of children who were aged 3 to 19 in East Boston, of which 654 had usable data. There's many variables measured here in this data set, but we're going to focus primarily on the outcome of FEV, and today we'll focus on age and smoking status to reflect our previous multiple linear regression lecture. As a refresher of this data set, we have a little scatter plot here where the green open-faced squares are non-smoking individuals and the solid blue squares are smokers. A few things to highlight here that you also may distinguish or differentiate from our effect modification or interaction lecture. Here we're looking at a multiple linear regression model without an interaction for simplicity. We can also note that there are no smokers, thankfully, before age 9, although it isn't great from a public health perspective to have that in the data set either. We can also note that generally there is this positive linear trend, but there does appear to be a difference or a decrease from this plot for the linear regression from a frequentist model for smokers. And that's just a super fast review and things we can keep in the back of our mind as we see these results. In our frequentist multiple linear regression, we had the following estimates of the coefficient table from our LM function. So for example, we see the intercept is 0.367. In other words, the average FEV for a 0-year-old who's a non-smoker, which isn't really sensible in our context given the fact that it's outside the range of our data and is extrapolation, and doesn't make a lot of sense to get an FEV rating on an infant regardless. We also have then down below here the corresponding 95% confidence intervals calculated around each of our beta coefficients, and we can just keep these in the back of our mind as we think through our future results from the Bayesian models. We're now going to explore three different sets of priors fit with the Bayesian approach for multiple linear regression. Specifically, we're going to illustrate and introduce the brms package in R for fitting these models because it has nice similar syntax to the LM and GLM functions we've been using throughout the semester for regression modeling. We'll also compare three different priors that we see outlined here, and we'll walk through these briefly in a second. Now, for each one of these, we're going to focus on the beta coefficients from our multiple linear regression model for age and smoking status. So for the first option, our quote-unquote non-informative prior, we're going to set each prior at a normal distribution at mean 0 and standard deviation of 1,000. If we think back to that FEV range of values in our plot, 1,000 goes well beyond sort of any of the observations we have or even the range of expected FEV values. So this gives a wide, diffuse range of possible values. We'll then assume in the second case that maybe we have an informative prior from some prior study or information. So for example, maybe we have some prior belief that the beta coefficient for age should be normally distributed with a mean of 0.2 and a standard deviation of 0.1. And likewise for smoking status, we might think that smokers have an FEV that's lower on average by negative 0.33 or a third with a 0.5 standard deviation. We'll then briefly show the challenges with poor prior specification by specifying a nonsensical prior for both age and smoking status with a mean at positive or negative 25 respectively and 0.1 standard deviations. Again, these are poorly specified because we don't have any FEVs that are as high as 25, and especially not for the rate of change for a 1-year increase. And also we can't have a difference of 25 for smokers if we don't even have that range in our values. But in the next slides, we'll walk through each of these examples and see how the differences do or don't appear in our posterior of our Bayesian inference. So let's start with that non-informative prior for a Bayesian multiple linear regression, MLR. As mentioned, we're going to be using the brms package to fit and evaluate our Bayesian models. We'll first start with our quote-unquote non-informative priors, which again, just as a reminder, have that mean, normal distribution mean 0, standard deviation of 1,000. We'll then assume default priors from the package for everything else, such as for the intercept or sigma, or mean square error from the model. Now, we'll break down the code here for just a second to tie in some of those concepts from the intro to Bayes lecture from before. The first thing we'll do is we will load that brms package to use, and then we'll use the brm function to fit our Bayesian linear regression model. Here we see in this top row, this is very similar to the syntax we have for, let's say, LM or even the GLM model, where we have FEV tilde smoke plus age, and we then specify the data set. The big difference now comes within this prior specification step. Now, there's a ton of different priors we could specify, both distributionally and putting these values in, and we'll look at 3 of them. But for this non-informative prior, we can see that we're going to specify each coefficient here as age, and we do have to denote what the model will look like for smoker here. We might look at the, let's say, the frequentist output before to get a little hint at what this should be. We can note as well that we have a class, which is B for our beta coefficients, and then we do specify that normal 0, standard deviation 1,000 here for each of our priors. We then have just some other details below where we will set our seed for reproducibility so we can recreate this analysis in the future. We'll define the number of chains to be 4, which is also the default currently for brms. And then we'll also define a warm-up of 1,000, or in other words, the burn-in length to discard from the total number of iterations, of which we'll do 2,000, both reflecting the defaults of the package. Let's assume we've turned our Bayesian crank and we fit our model with brms, and now we want to summarize the posterior. Fortunately, this is very easy to do, and the syntax is very similar to LM and GLM by using just the summary function for our model object, which we saved as mod1. Now let's break down some of the anatomy of this output here. At the very top, the first thing we can note is that we have some information about the type of regression we fit, in our case, linear or Gaussian. We also have information about link functions that may have been used, which we'll discuss in a later lecture. And we also have summaries about the number of draws, iterations, and burn-in periods. We also have a summary as well of the total number of iterations left over after we've discarded the burn-in or warm-up period of 4,000. Now, I think what's most interesting, probably, and most analogous to what we had before is the population level effects. Here this corresponds to the coefficient table we have from LM or GLM, but with some major differences of what's being summarized because this is a Bayesian model. The first thing we can note, and we described this a little bit in our Intro to Bayes material, but the estimate from our posterior, here is the mean from our 4,000 posterior iterations or draws. Now this can also be summarized by the median or mode or other values, and so we'll show we can do that later on as well. But it's important to note the default for brms is the average from the total number of post warm-up draws. One nice thing, though, that we can note is that the beta hat coefficients have the exact same interpretation as the frequentist multiple linear regression. Let's look at age, for example. For a 1 unit increase in age, we would say that there's on average a 0.23 increase in liters for FEV after adjusting for the other variables in the model, in this case smoking status. Now this is nice and because it keeps it easy to interpret this whether it's frequentist or Bayesian. However, one of the major changes we have is in this CI or credible intervals. And what the default for brms is an equal-tailed credible interval, which again is that they have an equal amount of 2.5% of the posterior chains below and 2.5% of the posterior chains above each of these given values. One of the advantages, though, I think relative to a frequentist analysis is that the interpretation is much more straightforward. We are essentially have a 95% probability that our beta coefficient truly falls within this interval, which again is different from that 95% confidence, or we are 95% confident that a beta coefficient is in this range. Because again, confidence doesn't have a nice, I think, intuitive interpretation. But we see here that it's the equal-tailed interval, so we'll also see in a few slides how we can calculate something like the highest posterior or density interval if we're interested in that. Now, something else we get from our output here is this r hat value, which gives us a good quick idea if we have decent convergence of our chains in our model, or if we should look at maybe some of the diagnostics we're going to visit upon in a second. Now remember, we want the rule of thumb to be less than 1.05, and some sources say less than 1.01, but in this case we've achieved an r-hat estimated of 1.00 when it's at least rounded to 2 decimal places, suggesting good convergence. Now, the final thing that may be of interest as well is that through our posterior chains in this model, we also estimate family-specific parameter sigma. Now, if we look at the bottom of the slide here, this is essentially going to be our square root of the MSE, or sigma hat y given x. This corresponds to that assumption we make in our linear regression model of homoscedastic variances, and we estimate it from the residuals of our model. Now we're going to visit how we can pull up some of the diagnostic plots or manipulate the posterior in different ways. The first thing we might want to do is check what priors we used or the defaults that were specified if we didn't specify anything ourselves. This is also quite easy to do with the prior summary function. Now, we're focusing on just the columns that are of interest for our given problem here, but we see in our given output we have different priors that were specified or have defaults. First of all, the default for our beta coefficients in the model, if we didn't specify anything, is this idea of what they just say is a flat prior. And you can look up more information in the help documentation for what that specifically means. For our interest, though, we can see that we have two user-defined priors based on our coefficients with those normal, mean 0, standard deviation 1,000. And if we want to see what they were using for the intercept and sigma, we see it has this student t distribution here, which again, you can look up more details in the BRMS output. But this can be a good sanity check if you see weird results, or if you just want to make sure you correctly specified the model you're trying to run with the appropriate priors. We may also want to look at some diagnostic plots of our posteriors. For example, we might want to look at the density and the trace plots, and this is what the default comes out of from the plot function in BRMS. For example, we see that we have a density plot for our intercept beta hat naught. It has this nice symmetric kind of shape, and we can see that here we can estimate, let's say, the mean or the median from this kind of density or distribution. We likewise can do the same thing for beta hat 1 or for smoker, beta hat 2 for age, or for an estimate of sigma hat, that y given x, our assumption of equal variance. Now likewise, we may also want to see convergence more diagnostics, and that's where we have the idea on the right-hand side of these trace plots. Again, we're looking for random noise, where it looks kind of like it's just exploring across this random space in a kind of convergent horizontal space. And we see this as the true case for all 4 of our variables that we estimate here, the 3 beta coefficients and sigma. Now, remember, if we see something that looks actually like it's following some sort of pattern or not really converging in a horizontal space, that could show concern about convergence, and either we need to reevaluate our priors, the model, or maybe our data doesn't support what we're trying to look at. We can also note here as well that because we fit 4 different chains, we actually see various iterations of blue showing equal kind of random noise, which is really encouraging for these models. So this is actually what we hope to see. In practice, you may see that there's issues with all or even just one of your coefficients with convergence, which we would want to diagnose and try to address and troubleshoot in those cases. Another plot we may want to quickly look at is the autocorrelation, which again just gives us an idea of how efficient our estimation is doing. Ideally, we see something that drops quickly with increasing lag, and here we see that we have something that is broken down by each coefficient or each parameter we're estimating, and each row represents then a different chain. The good news here is that all of these look like they have a quick L shape of a quick decrease and then pretty low correlation here. Now this is also easy to plot if we use the MC plot function and we specify the type to be the autocorrelation. As mentioned, the output for BRMS with the summary function shows the equal-tailed credible intervals. Now instead we may want to do other summaries such as the highest posterior density or HPD interval. In other words, that's the narrowest interval that will include 95% of the posterior. The advantage here is that we'll always include the mode, but it doesn't necessarily include the same interval or range as those equal-tailed credibles, especially if we don't have a symmetric posterior. Now, in this case, we can use a different package, the Bayes test R package, using their HDI or highest density interval function. All we have to do is provide it with our model and the desired confidence interval, here 95%, and we see that it gives us the following output. Now, because everything looked fairly symmetric for our trace plots, the equal-tailed credible intervals are quite similar here, and so we can actually see that really the only difference is I would argue, between smoking status out to these 2 decimal points, where it's not that different, just 0.01. But this shows an example of how we can get these interval estimates if we do desire something different from the default of BRMS. Now, we also might want to extract actually the raw posterior chains from our MC process. And this is also actually pretty easy to do as well. Now, we have some code here. There's various forms of this as_draws function. Here we're using as_draws_df because we want to extract it as a data frame to look at. Now, we can just take a sanity check here to confirm that there are 4,000 rows or 4,000 pooled iteration across all the chains. We can look at, let's say, the first 4 and the last 4 here in the output below. Now, a few things with the default sort of structure or class type here. We do see that there are, at the very bottom, a few hidden reserved variables. We have the chain number 1, 2, 3, 4, iteration 1 to 1,000, and the draw numbers. These are things we could also look at if we were interested in summarizing that information. At the very top here, it tells us that we have 8 iterations from 2 different chains across 6 different variables. And here, for the sake of our class, we can focus on just the coefficients or parameters of interest that were estimated here, looking at how they vary from iteration to iteration across our chain and process. The L-prior and LP are more parameters estimating the process of the estimation of the MC that we won't discuss in this lecture. Now, the reason we might want to extract our posterior chains is because we might want to do either manipulations or summaries with them for specific posterior probabilities. And this is really easy to do once we've extracted our posterior iterations. For example, if we want to calculate a posterior probability, oftentimes abbreviated PP, we can just take the posterior chains and estimate the proportion of them that meet that criteria. So let's just say, for example, we're interested in our coefficient for beta for smoking being greater than 0, less than 0, or less than -0.1. We know that for the frequentist models, we have to do a couple different steps for testing these hypotheses, calculating the test statistic, appropriately defining the test statistic for a given null. And here we can see that it's as easy as just taking the average proportion of times that we have the 4,000 iterations of our beta coefficient for smoker being greater than 0. So here we see it's pretty unlikely that beta coefficient or smoking has a positive effect from our posterior estimates of just 0.4% of the time. Likewise, 1 minus that will get us the probability that smoking is less than 0, which is most of the time 99.5%. Or if we were interested in saying, well, maybe smoking reduces it by at least 0.1, what's the probability of that? Well, then we still see here at the bottom value that we have 90.425% probability that smoking is less than -0.1. In other words, it's more likely to be larger than a decrease of -0.1 relative to non-smokers. But again, this is really easy to estimate for any beta coefficient or probability. We can also easily estimate the posterior probabilities for other types of combinations of our posterior variables or other manipulations. For example, since we're doing a regression model, we might be interested in testing a specific hypothesis that a 15-year-old smoker has an average FEV that is less than 3.82 by estimating the FEV from each of our 4,000 posterior iterations. In other words, it's like we're using 4,000 different regression equations, but estimating that to show the uncertainty across all of these values. Now, the 3.82 simply just comes from the average expected FEV for a 15-year-old non-smoker from the Frequentist MLR to use as an example here. But we can see from our model, all we have to do is extract each of the posterior estimates for our beta for the intercept, for smoking status, since this is a 15-year-old smoker, unfortunately, and then add 15 times their age, because again, it's just like a regression equation, beta hat age times x. And here we're essentially going to have 4,000 estimates of that average FEV, and we're going to ask, is it less than 3.82? Which we can then see happens 99.9% of the time. In other words, the average FEV is expected to be less than a non-smoking 15-year-old almost all the time throughout our various iterations of our posterior. Now, another thing we can do once we've extracted our posterior iterations is also use different types of summaries for our point estimates. So for example, we talked about maybe using the median instead of the mean. And again, this is pretty easy to do. We see that if we apply, like let's say an apply function, we can specify median instead of the default mean that is being used in BRMS, and we get the estimated coefficients here. Now in this case, because again, things look pretty symmetric, we don't have a lot of difference between our mean and median. But in other cases, we may have a skewness in our posteriors that may make us think that the median might be a more appropriate estimator than the mean. So that wraps up the non-informative prior and sort of the walkthrough of all the functionality. We're just going to briefly turn our attention to looking at the results and similarities or differences for an informative prior with the Bayesian MLR. Now again, remember, we had this idea that maybe we had prior data that suggested we already had some estimate for what we think the beta coefficient for age and smoking status should be, and we'll assume that maybe it's from a prior study. Now, here we can see that it's really easy to just modify the code we had before to update those priors in our set prior part of the brm function. And we see that we really just are specifying whether it's normal 0.2, 0.1 for age or negative 1/3, 0.5 for smoking status. Now, as we turn our Bayesian crank here, we see we get a very similar set of output as we had before. And in this case, even though we gave it a more informative prior, we actually see that our results are extremely similar to the non-informative priors. In this case, we didn't see a major difference in our results, and this is because, well, partially that our priors actually fairly well align with the observed data, or the likelihoods, and also partially because we didn't specify them to be so overwhelmingly powerful that it actually ignored essentially the data and the likelihood. So we still have the ability for the likelihood to impart its own influence on the prior as well. However, this won't always be the case. We did note we were going to look at a nonsensical, poorly specified prior for the Bayesian MLR. For example, let's examine the strong priors that have a more extreme and, quite frankly, nonsensical effect and small standard deviations of positive 25 mean for beta coefficient for age with a standard deviation of 0.1, and for smoking status, a decrease for smokers of 25 in FEV by liters and a standard deviation of 0.1 liters. Now we'll assume default priors for everything else, like the intercept and sigma. Now, again, the nice thing here about BRMS is that it's really easy to just change this prior out, and like we should explore a range of different prior specifications, although realistically we should look at something so nonsensical. But let's assume we turn our Bayesian crank here as well, and we look at the poorly specified model summary. Now, as our example here, we see that essentially we are doing terribly at estimating things. The results are very different from our prior models. Essentially, in this case, the priors have overwhelmed our observed data, and the posterior estimates are really more reflective of the prior than anything we've observed. We can also note that the intercept is quite different as well because it's trying to account for the differences induced by having the negative 25 prior on smoking status and the positive 25 prior on age. Now we can note that there is a little bit of a change. For example, age is pulled slightly away from 25, but nothing meaningful here. Now what may be slightly concerning is things like our hat values suggest there are still adequate convergence. So just because we did poor prior specification doesn't mean the model tells us or warns us about it. So we do still need to be critical thinkers when we choose and specify priors and determining how we set them and interpret the results to make sure they make sense. But with that, let's close with a brief summary. We just discussed Bayesian approaches to linear regression and how they can give us flexibility to incorporate prior information and to calculate different summaries like posterior probabilities instead of p-values or credible intervals instead of confidence intervals. And quite frankly, they have more intuitive interpretations. Now, other Bayesian languages exist in packages out there, and they can also be used to fit regression models, so feel free to explore different options and what works for you. Now, just as a reminder, in practice, whenever we're fitting these Bayesian models, we should always consider multiple reasonably specified priors. In our example, our final poorly specified prior illustrates the dangers that can happen if we are not careful, but realistically, we should look at a range of different things to see if they're fairly robust like our first two options were, or if things change with respect to our posterior estimates. But with that, thank you for your attention, and I hope you have fun doing some Bayesian linear regressions.